So in this video, we're going to talk about crystal field theory, which is a pretty simple theory, but it's also very useful. And this is used to explain certain spectroscopic and magnetic properties of transition metal complexes. So what sorts of things would we like to be able to explain here? First of all is that nearly all transition metal complexes are colored. So just to name a few examples, in aqueous solution, the hexaquo cobalt salt is pink, nickel is green, and cobalt is blue, just to name a few examples. And yet zinc is an exception. Zinc is colorless. In aqueous solution, zinc compounds are colorless, and in the solid state they're white, but they're definitely not colored. So what is special or different about zinc? A second thing is that the color depends upon the nature of the attached ligands. So for example, in aqueous solution where you're going to have 6 waters coordinated, nickel is green. And yet if you add 15 molar ammonia and make the ammonia concentration high, the color changes to violet. So the nature, the color of the complex very much depends upon the nature of the attached ligands. The third thing is that some compounds do not have the predicted number of electrons. So for example, if we look at two complex ions, both of which contain iron 2, if you look at the hexaquo ion, that ion is paramagnetic. And yet, if you look at the ferrocyanide ion, that's diamagnetic. And you say, wait a minute, how can that be? Because based on what you know up to this point, the only diamagnetic ions are the D10 ions, right? Diamagnetic ions where you have all the d orbital electrons paired up. So iron 2 is certainly not a D10 ion, it's only a D6 ion. So how can this compound be diamagnetic? So what's going on here? So for a bare metal ion, the d orbitals are said to be degenerate. What this means is that they all have the same energy. But in a complex ion, these orbitals wind up getting split up into 2 groups. So let's look at some very simple drawings of the d orbitals. So the d orbitals get split into 2 groups. These 3 belong to the same group, and these 2 belong to the same group. All right, so you have the x and y, which is between the x and the y axes, and you have the xz, which is between the x and the z axes, and you have the yz, which is between the y and the z axes. And you have the x squared y squared, which is on the x and y axes, and the z squared, which is on the z axis. So what's common about these 3? What's common about these 2, and why are they different? What's common about these 3 is that they all place the orbitals between the axes, whereas these are on the axes. So let's say that we have some octahedral ligands that are trying to come in and they're trying to bind, and the ligands bind to the metal by donating electrons. Well, some of these orbitals might have electrons on them. Depends upon how many electrons the particular metal ion has. So, and that's what makes these raised in energy. So these 3 get lowered in energy, and these 2 get raised in energy. So the x squared, y squared, and z squared are on the axes, or oriented along the axes or on the axes, and are raised in energy. These form a doubly degenerate set called the EG orbitals. And the XY XZ and YZ were oriented between the axes and are lowered in energy, and these form a triply degenerate set called the T2G orbitals. Just think T for triplet. There's 3 of them. Okay, so this is not a symmetric split. Well, in a way it is, but it doesn't seem like it at first. The T2Gs, these are your 3, X, XY, XZ, and YZ, get lowered by 2/5 the field splitting. Now delta O is the symbol that we use for the field splitting. Just think O for octahedral. Okay, so these are lowered by 2/5 the field splitting, and these are raised by 3/5 the field splitting. So the idea is this. All right, so we're splitting off the energies of the d orbitals into 2 groups. So it turns out then that for many of these ions you can write two possible electron configurations. Okay, we have what we call the high spin case, and we have what we call the low spin case. The high spin case has the maximum number of unpaired electrons. That is, when we write out an electron configuration for a high spin case, every orbital has to have 1 electron before they can begin pairing. This gives the same number of unpaired electrons as if there were no field splitting. And this is going to be favored by complexes with a small field splitting. We'll talk more about this. In the low spin case, the T2G orbitals are completely filled before the EGs. This is going to be favored by complexes with a large splitting. Right, so let's say we were going to write the configuration for a high spin ion. Then we add 1, depending upon how many electrons we have. We put 1 electron. We don't pair them up until every orbital has 1 electron. So if we were going to write a high spin, one more time, these are the T2Gs and these are the EGs, right? We're writing high spin, we would go 1, 2, 3, and then we pump up here, we jump up here, and we go 4 and 5. Then we come back down here and start to complete it out. 6, 7, 8, 9, and 10. And that's how the order in which you would fill these orbitals to write a high spin ion. Now, if we were going to do low spin, one more time, T2Gs and EGs, we fill all these first. We put the maximum number that we can down here. All right, so we would fill the orbitals this way. We would go 1, 2, 3, and then we have to start pairing them up, but we stay down here. 4, 5, 6. Then when these are completely filled, we jump up here. 7, 8, 9, and 10. Okay. So high spin case. So what's the difference? What's the difference? It's a function of how big is the field splitting, right? If you have a really small field splitting, then we're splitting off the orbitals, so splitting is not so high, not so big. That's going to favor high spin. If this field splitting is really big, it's going to favor low spin. There's an energy penalty either way once you get past a certain number of electrons. If you put them down here, the energy penalty is that we're going to have to pair them up. And if we put them up here, then the energy penalty is that it's going into a higher energy orbital. It depends on which is worse, right? And so the bigger we make this field splitting, more likely you are to be low spin because these get lowered. These are getting lowered in energy. It's an energy trade-off. If this is low enough to offset the pairing energy, then they'll go down here. If the field splitting is not so big, then once you get past a certain number of electrons, you say, okay, if I go down here, I'll have to pair it up, but if I put it up here, then I get an orbital to myself. So it's a trade-off either way. We'll come back to this in a minute. All right. So let's walk through some of these electron configurations. So for the first three ions that you could have, D1, 2, and 3, there's only one configuration possible, right? So we start just like we were writing an electron configuration without any splitting at all. All right, you always start at the bottom. You start with the lowest energy orbitals. We have empty orbitals. If this is wide open, there'd be no reason to jump up here. And by the way, all I did was show the same thing on one line here instead of showing it vertically. I did it horizontally to save space. These three are grouped together because they have the same energy. These two are together because they have the same energy, the T2G and the EGs. So we got one electron. There's no reason to jump up to the higher energy orbitals. So for D1, your electron configuration is simply T2G1. That's the way you'd write it. Okay. When we get to D2, we're going to add a second electron. So it's simply T2G2. And when we get to the third electron, it's simply T2G3. All right. So those are our D1, D2, and D3 ions. It's not until we get to the D4 is the first case where we have two configurations, right? So if we're going to write the high spin ion, we'll simply go 1, 2, 3, and 4. Okay? So our electron configuration for the high spin would be T2G3, EG1. If we write the low spin, remember to write the low spin, all the electrons, these are filled first. The T2Gs are filled first before we can jump up here. So we're going to go 1, 2, 3, and then we come back and put the fourth one and start to pair them up. So one more time, it's an energy penalty either way. So it's a matter of which has the lesser energy penalty, right? If we put it up here, the penalty is that it's going into a higher energy orbital. And if we put it down here, then the penalty is we have to supply pairing energy. So it depends, which case you get depends upon how big the field splitting is. If the field splitting is really small, okay, and you say, May, going up to one of these higher energy orbitals is not so bad. We'll rather do this. If the field splitting is really big, then the fourth electron comes along and says, geez, if I go up here, I'm going to have to go all the way up here. I'll just stay down here and pair up. But there's an energy penalty either way. So when we go to the high spin, when we go to the D5, now we got 5 electrons. We're just going to add one more electron. So our D5 high spin will be T2G3, EG2. Okay, we just added one more EG electron. Now the low spin will go 1, 2, 3, 4, and 5, and that gives us the configuration T2G5. So we can either go T2G3, EG2, or we can go T2G5, high spin, low spin. So we go to the D6, high spin. We'll go 1, 2, 3, 4, 5. Now once we get past 5, now we have one electron in every orbital. Now we have to start pairing them up. So we come back down here and put one more in the T2G. So our configuration is T2G4, EG2. That's the high spin. Whereas if we do the low spin, we completely fill up the T2Gs first. So we would go 1, 2, 3, 4, 5, and 6. And what's our configuration? T2G6. Well, do you see what I see? All the electrons are paired. This would be diamagnetic. And this is one of the things that we sought to explain when we started this discussion. Why are some ions diamagnetic even though they're not D10 ions? And if you look at iron, iron 2 is a D6 ion. So low spin D6 ions are diamagnetic. All the electrons are paired. So we go to D7. So now we add one more electron, so we would write it this way. We would say 1, 2, 1, 2, 3, 4, 5. Then we come back down here and start pairing them, 6 and 7, right? So our configuration is T2G5, Eg2. And the low spin, we'd add one more electron. The T2G is completely filled. We add one more electron to the Eg. So our electron configuration is T2G6, Eg1. So for the 8, 9, and 10 ions, D8, D9, and D10 ions, there's only one configuration possible. All right. So for D8, we would write it as we would, to fill out this out, we would say 1, 2, 3, 4, 5. Then we have to start pairing them up, 6, 7, and 8. So that would give T2G6, Eg2. But if you tried to write it low spin, you would do the same thing. If you tried to write it low spin, we would go 1, 2, 3, 4, 5, 6, and then jump up here and go 7 and 8, which gives you the same configuration. So there is no high spin, low spin for D8. Okay, there's only one configuration, that's T2G6, Eg2. When we get to the D9, we're simply going to add one more electron, so it's Eg3. And when we get to the D10, we'll add one more electron, still complete the filling of the orbitals, and that's Eg4. And note that this ion is going to be another diamagnetic ion, D10. So D10 is diamagnetic, regardless of whether the orbitals get split off or not. Okay, there's 2 electrons in every orbital. So let's talk about now the crystal field stabilization energy, CFSE. What is this? It's the energy change associated with the formation of a complex ion relative to the case with no field splitting. In other words, what's the energy change associated with the formation of the ion? So if we have, one more time, we start with D1. We'll go back through these cases, starting with D1. So the D1, we simply got the 1 electron in the T2G orbital. So what's our energy change? Remember that one more time that these T2G orbitals were lowered in energy by 2/5 to field splitting. And we're putting the negative sign there because that's a negative energy change. In other words, that's an energy benefit. It's energy that we are getting out. So what's our change in energy, or our stabilization energy? It's simply 1 electron lowered by 2/5 to field splitting, right? All the T2G orbitals were lowered by 2/5 to field splitting. So our stabilization energy, one more time, is simply 1 electron in an orbital that's lowered by 2/5 to field splitting. Okay? For the D2 ion, we're simply adding another electron. So that's negative 2/5 times 2 times the field splitting, or 4/5 the field splitting. And for the D3 ion, it's simply 3 times 2/5 times the field splitting, or negative 6/5 the field splitting. So again, the D4 is the first case where we have two configurations. Let's do the high spin first. So what would be the stabilization energy for the high spin case? We've got three electrons that are raised, or excuse me, three electrons that are lowered in energy and ones that's raised in energy. You have three electrons lowered by 2/5 the field splitting plus one electron that's raised by 3/5 the field splitting, right? So that's minus 6/5 plus 3/5, or negative 3/5 times the field splitting. Okay. Or if we did the low spin, all the electrons are down here, but we had to pair them up. We have to supply a pairing energy. This is energy that's required. All right, so we got 4 electrons that are lowered by 2/5 the field splitting, but we have to supply a pairing energy. Okay, and that's positive energy. This is energy that we get out. This is energy that we have to put in. So this comes out to be negative 8/5 delta O plus the pairing energy. So we go to D5. If we go to a D5, all right, so what do we got? We've got 3 electrons here. We have 3 electrons that are lowered by 2/5 the field splitting, plus 2 electrons that are raised by 3/5 the field splitting. Well, guess what? 3 times 2/5 is equal to 2 times 3/5. So these cancel each other out. The energy gain here, the energy that we get out here is negated by the energy that we would have to put in here. It adds up to 0. So there is no crystal field stabilization energy for the high spin D5 case. Now we go with the low spin case. We have, one more time, as low spin, we put all the electrons into the lower energy orbital. So it's great news. All you electrons get lowered in energy by 2/5 the field splitting, so 5 times 2/5. But bad news is we have to supply 2 pairing energies. So that's our stabilization energy, negative 10/5 times the field splitting, plus the penalty of the 2 pairing energies that we had to supply. If we go with D6, then we move on to D6. So our high spin D6, what do we got? We've got 4 electrons down here and 2 electrons up here. So we have 4 electrons that are lowered by 2/5 the field splitting, plus 2 electrons that are raised by 3/5 the field splitting, right? So negative 8/5 plus 6/5 comes out to be minus 2/5, and you say, whoa, wait a minute, stop. We had to pair up 2 electrons. So why isn't there a pairing energy here? Because the stabilization energy is the energy of this ion relative to what we would have to put in if there were no field splitting. Now, if there were no field splitting at all, and we just had the 5 degenerate d orbitals, and we were following Hund's rule, we would still have to pair up 2 of the electrons, right? Once you get past 5 electrons, you have to start pairing them up, regardless of whether the orbitals are split off or not. So here, you don't include the pairing energy, okay, because the electrons would be paired anyway. All right, so when we write the low spin D6, we're going to have, we put all the electrons down here. So the great news is, guess what? Every single electron gets lowered in energy. So 6 times 2/5 times the field splitting. Bad news is we have to pair them all up. All they're paired. So we have to supply 2 pairing energies. And one more time you say, oh, wait a minute, we're supplying 3 pairing energies. That's true, but 2 of them would have been paired, 2 electrons would have been paired to begin with. if we were following Hund's rule with no field splitting, we would have had to pair up 2 electrons regardless. So it's plus 2 pairing energies, not 3. So we go to the D7 case, high spin, right? So we're going to have 1, 2, 3, 4, 5 electrons that are lowered by 2/5 of field splitting, plus 2 that are raised by 3/5 of field splitting. So let's see, minus 10/5 plus 6/5 is minus 4/5, and we don't have to supply a pairing energy. Why? Because we would have had to pair these up anyway, regardless of the splitting. We would have had to have paired electrons anyway. All right. So we get to the low spin D7. So we have 6/5. We have 6 electrons lowered by negative 2/5 times the field splitting, plus 1 electron that's raised by 3/5. And we have to supply 1 pairing energy. Now these would already have been paired to begin with. So we're only having to supply 1 pairing energy above and beyond what we would have in the case of no field splitting. So we're having to supply 1 additional pairing energy. So our stabilization energy is minus 9/5 times the field splitting plus the pairing energy. So then we get to the D8 case. So remember, for the 8, 9, and 10 configurations, 8, 9, and 10 ions, there was only 1 configuration. Right, so for our stabilization energy for our D8, we have 6 electrons that are lowered by 2/5 of field splitting, and then 2 electrons that are raised by 3/5 of field splitting. So what? Minus 12/5 plus 6/5 is minus 6/5. And we don't have to supply any pairing energy because these would have been paired in the absence of no splitting. If you write it out with Hund's rule and following Hund's rule, you'd still have to have 3 pairs of electrons. So we don't have to supply pairing energy. For the D9 case, we're going to add 1 more electron, so now it's 6/5 times minus 2/5 times the field splitting. Now we have 3 electrons. We've added 1 more electron. Now we have 3 electrons that are raised by 3/5 the field splitting. So let's see, minus 12/5 plus 9/5 comes out to be minus 3/5. Okay, and we don't have to supply a pairing energy because all these would have to be paired in the absence of no field splitting. And we get to the D10. We have all the electrons filled. We have all the orbitals filled. So 6 electrons lowered by 2/5 of field splitting, plus 4 electrons raised by 3/5 of field splitting. Well, minus 12/5 plus 12/5, it adds up to 0. So here's going to be another case where we have no crystal field stabilization energy, right? So for the D5 and the D10 ions, there is no crystal field stabilization energy.